If you fell into a black hole and somehow carried a memory recorder that could track every microscopic state of matter you touched, would the information you lose have to disappear, or could it somehow get stamped into the horizon itself like a firebreak that prevents total chaos from spreading? Here's the misconception. People think the event horizon is just a point of no return, a simple boundary where physics gives up. But what if the horizon is more like a living interface, an encoding surface, where entropy isn't merely a measure of ignorance, but a literal ledger of what reality must look like on the inside? Today, we're talking about an idea so counterintuitive, it almost sounds like a contradiction. The impossible black hole firebreak, where the growth of entropy is constrained in a way that forces the horizon to remain coherent, even when everything else seems destined to become thoroughly scrambled. It's not a firebreak made of brick, it's a firebreak made of information. Before this concept can make sense, we need the landscape it grew out of. In ordinary thermodynamics, entropy counts the number of possible microscopic configurations compatible with what you know: heat, death, irreversibility. These are all entropy stories. Then black holes arrived and turned those stories into puzzles. If you throw matter into a black hole, the external universe loses details. Yet, paradoxically, black holes have temperature and entropy. In the 1970s, Bekenstein argued that the black hole's entropy should be proportional to the area of its horizon, not its volume. Hawking showed black holes evaporate through quantum effects, emitting radiation that seems thermal, meaning it appears to carry no specific information about what fell in. So the before state of the debate was this: either information is truly destroyed, contradicting unitary quantum mechanics, or information somehow returns in the radiation, which clashes with the featureless thermal character of Hawking's result. Now for the deep dive. Imagine the universe as a vast book written in microstates. Entropy is the number of possible pages that match the same sentence you're able to observe macroscopically. For black holes, the event horizon becomes the page where the relevant constraints are applied. The horizon reality idea says, the horizon isn't just a geometric boundary. It's an information processing surface governed by quantum gravity. And entropy isn't only an accounting tool. It actively constrains what kinds of internal histories are even allowed. Enter the notion of a firebreak. In many proposals for resolving the black hole information problem, the key challenge is that entropy should increase smoothly as the black hole forms, then eventually must decrease or encode information in a way consistent with unitarity. But smooth evolution alone can lead to contradictions. If information is hidden behind a horizon in a naive way, quantum entanglement patterns would imply too much scrambling, producing an internal breakdown of the horizon's sevoaxial description. Put differently, if the entropy bookkeeping is pushed too far, the horizon can't keep acting like a normal place where physics is predictable. The firebreak idea introduces an abrupt constraint, an interface property that blocks an uncontrolled spread of inconsistency. Think of it like a forest fire plan. You don't stop every spark from existing, but you build a break that prevents the entire region from burning as a single connected blaze. Here, instead of flames, the risk is runaway entropic growth that would force two different descriptions, quantum unitarity outside and Cerro-Anolaros, to disagree. The impossible black hole firebreak is the claim that, while the interior might be wildly complex, the horizon must enforce a specific entropic structure. This structure is impossible only if you assume the horizon is just a passive boundary. If the horizon is an encoding surface, the entropy constraints become a mechanism that preserve coherence. The horizon remains a consistent locus for quantum information transfer. The deeper meaning is that horizon degrees of freedom must do the encoding work. When the black hole forms, information about infalling matter is not carried away as detailed classical data. Instead, it becomes part of a quantum pattern distributed across horizon microstates. As Hawking radiation proceeds, the entanglement between the radiation and the remaining black hole evolves. The firebreak is an enforcement of the allowed entanglement structure, an entropy-driven rule that prevents contradictions like the interior looks smooth, while entanglement insists it should be violently inconsistent. Where does the analogy help? Picture a movie projector. The outside observer sees a thermal glow, frames that look statistically similar, like a blurred stream of pixels. But the projector's film reel, its microscopic state, still determines which frames can appear. Entropy is high because many microscopic reels can produce similar coarse-grained visuals. Yet the horizon firebreak is the mechanism ensuring that only reels consistent with the quantum rules are realized, so the projection never violates the underlying coherence of the system. The horizon isn't the image on the screen. It's part of the projector that determines what the screen is allowed to show next. So why should you care beyond black holes being cosmic troublemakers? Because the same underlying question, how entropy and information relate, sits at the core of modern physics. If the horizon is an interface where entropy encodes reality, then entropy is not merely a measure after the fact. It becomes a constraint on what the universe can do. This affects how we think about quantum gravity, because any consistent theory must explain how symptotical space-time emerges from entanglement and how information is preserved without erasing the apparent thermality. It also shapes our understanding of error correction in nature. The idea that horizons behave like error-correcting surfaces suggests that information might be stored redundantly in a way that protects it from certain local disturbances. That's a profound bridge between abstract black hole thought experiments and concrete quantum technologies. If nature uses encoding tricks at the horizon scale, perhaps we can learn principles for designing robust quantum information processing. And there's a philosophical knock-on effect. If entropy encodes horizon reality, then where information goes isn't a simplistic motion from one place to another. Instead, information is bound to relational constraints. What correlations are permitted by the structure of the horizon? Reality itself becomes, in part, the set of allowed correlations. So we circle back. We began with the misconception that the horizon is just a point of no return where physics becomes mute, but the impossible black hole firebreak suggests something subtler. The horizon remains meaningful because entropy and entanglement are actively enforced there. The horizon isn't passive. It's an encoding interface whose entropic structure prevents an entanglement mismatch from spiraling into a contradiction with quantum mechanics. In the end, the black hole information problem is not just about saving data. It's about learning how the universe prevents impossibilities from spreading, how entropy can be both a measure of ignorance and a rulebook that ensures the horizon stays real. If you want more deep dives into the weird interfaces where reality is written, subscribe now.